All right. I think it's on the hour wherever you are. Who knows what time zone you're in, but wherever it is, it's on the hour. So I think we can go ahead and get started. So before I introduce our speaker today, I want to remind everyone that you can ask questions either by entering them into the Q&A function if you're watching on Zoom, or if you're watching on YouTube, you can enter it into the chat on the side next to the video. And there will be a couple of breaks during the talk where I can convey, as the moderator, I can convey your questions to the speaker. And so with that, our speaker, oh, and also there will be after the seminar, a post-seminar discussion with the speaker where you'll have opportunities to interact with her one-on-one, or well, not one-on-one, but you'll have opportunities to interact with her directly. And we'll post the link to that and the password so that you can get in, and so that trolls can't, at the end of the talk. So with that, it's my great pleasure to introduce Jelena Vučković. So Jelena is the Jensen Huang Professor in Global Leadership in School of Engineering and Professor of Electrical Engineering at Stanford University. So she's done really leading work and groundbreaking work in integrated nanophotonics, quantum optics, cavity QED, and in particular, a lot of work with solid state optical defects of many different kinds, a whole different variety of optical defects, including quantum dots, defects in all kinds of defects in diamonds, and now defects in silicon carbide as well. Jelena has a number of awards and honors, and I won't list them all here, but just a few of them. She's currently the director of QPharm at Stanford. She is a fellow in Optical Society of America, APS, and IEEE, which is pretty impressive. And she's a recipient of the Humboldt Prize, as well as the PCASE and a few different young investigator awards earlier in her career. And so we're really looking forward to your talk today, Jelena. So please go ahead.
Thank you very much, Shimon. Thank you, everyone, for the invitation. It's a great pleasure to be here. And this is an AMO seminar. I work on semiconductor systems, as you already heard from the introduction, but I view it as AMO in semiconductors or solids. So I hope you'll enjoy a little bit of the different flavor of AMO that we do. And I'd like to start with a question, actually, that is kind of motivating a part of our work, which is whether we would eventually be able to build semiconductor quantum simulators and possibly even quantum computers. And you're all familiar with the work, interesting work, exciting work ongoing on the superconducting qubit platform, also a variety of AMO platforms where people have managed to scale the systems to several dozens or several hundreds of qubits for this purpose. But what we would really like to do is kind of bring this down to chip scale, use a semiconductor such as diamond or silicon carbide or maybe some other semiconductor, kind of scale everything down, but do the same types of experiments. And kind of, that would enable us also to reduce the infrastructure and overhead that we have in our experiments. It's still not just a chip, of course. There is still a lot of lasers and optics, but it's simpler. We can still integrate a significant portion of that on the chip itself and reduce the complexity of the experiment. So today, I will talk primarily about the two platforms that we're doing at the moment. As you heard from the introduction, we worked on a variety of different systems in the past, including gallium arsenide quantum dots, indium arsenide, gallium arsenide quantum dots. But right now, we're primarily focusing on diamond and silicon carbide. And here you see some devices that we made in these two materials. And I'll tell you more about our choice of qubits there. And this background that you see here is also a silicon carbide chip that I'll be talking about. So here we're able to make very high quality photonics, but of course that's not enough to build quantum systems and technologies that we're interested in. So we also have our choice of qubits, and for us, qubits of choice are optically interfaced semiconductor spin qubits. So for those of you who are more from the superconducting qubits platform side, the physics of this system that we work on is pretty much the same as Josephson junctions inside of the microwave cavities. For us, the system is this color center or or spin of an electron inside of an impurity in semiconductor, as you see here, and then you have a resonator around it. And of course, this is the same as the atomic physics platform, where you have a naturally trapped atom inside of a resonator, so sort of cavity QED, traditional cavity QED platform that many of you work with. But for us, atom is this naturally trapped impurity inside of a wide bandgap semiconductor. So here, for example, you see an extra thin atom inside of a diamond lattice, and you see two vacant carbon spots. Same configuration would hold for silicon vacancy in diamond, where you would have just silicon impurity and then two vacant carbon spots and variety of other impurities that we work with. So we don't really need to trap this optically or magnetically, as opposed to atomic physics experiments where people work with neutral atoms or ions. Everything is already trapped inside of the crystalline structure. But of course, then there is a price you pay, and you have to worry about that interaction with the environment. It's not vacuum anymore, but that reduces complexity. So relative to superconducting platform experiments, again, I said physics of these cavity QED systems is the same, and we can do the same experiments, and we've demonstrated the same experiments on AMO platform and solid state cavity QED platform and superconducting platforms in the past. But there are differences, right? So for us, atom is not in the vacuum, interacts with the environment. So you have to worry about a variety of dephasing effects that occur. Relative to superconducting platform, our system is much, much smaller by a factor of 1,000 or even more than that, because we operate at optical frequencies. So we can scale everything down. But that also means that you have to use more sophisticated nanofabrication techniques to implement everything. So, just inserting one atom at a special spot without damaging lattice is pretty challenging, and I'll show you some ideas and some work that we've been doing towards solving those problems. Then you have to fabricate these structures that are much smaller, so nanofabrication is more sophisticated. But we work with semiconductors, which is good, right? So we work with kind of more traditional materials, in particular silicon carbide, which is pretty common material in electronics. Then we can possibly operate systems at higher temperatures, not at room temperature, but few Kelvin temperatures, which means that we can use different instruments. We don't really need dilution refrigerators. For some of these atoms, closed cycle cryostats are sufficient, which kind of simplifies, again, the infrastructure and the experiment a little. Also, these systems already have excellent optical interfaces. So we work with atoms with impurities that have excellent optical interfaces. So we don't really need to worry about solving quantum transduction problem, for example, because once we have this atom inside of the cavity, we can interface it to optical fiber or other parts of the system, and quantum transduction is not really necessary anymore. And maybe kind of an interesting point to add here is that for many of these systems, although they haven't really scaled nowhere near the superconducting systems or some AMO platforms, the number of 2-qubit gate operations that you can do per electron spin coherence time exceeds number of operations that you can do, for example, for superconducting qubits. Of course, the systems have not scaled yet for the reasons that I'll describe in a moment, but once they scale, this is of course very preferable. So that's what we work with. And I mentioned already that this field is very much like atomic physics, right? So you can pick your atom or pick your ion, and then pick a platform, and you can implement photonics and do your experiments. And then when you shift to a different atom or ion, then you have to build a new setup and get a new laser and so on. So this chart here shows variety of color centers in diamond that we and others work with. And at the moment, most of the interest and work is on this group 4. Inversion symmetric diamond color centers. They have a configuration that I just showed you previously. So you have 2 missing carbon atoms in diamond, and then you have an impurity sitting between these 2 vacancies. And that impurity is group 4 atom. And we and others have done work on silicon, germanium, tin, and recently there was some work on lead. And this inversion symmetry is pretty important because to the first order, the system is immune to basically DC start shift and static electric field in the system. And that means that you can actually, as opposed to nitrogen vacancy center in diamond, bring it closer to surfaces, embed it easier in the structures, and make photonics kind of more scalable in this platform. Initial experiments have been done on silicon vacancies. Then there was quite a lot of work on germanium vacancies, and recently we and a few others group have focused primarily on tin vacancies in diamond. And we like tin vacancy because it has a larger ground state splitting, much larger ground state splitting than silicon vacancy. So 850 gigahertz relative to 50 gigahertz, which means that you don't really need to cool system down to really millikelvin temperatures to avoid mixing, dephasing actually, and mixing between ground states. So for silicon vacancy, for example, all of the state-of-the-art experiments have been done at millikelvin temperatures in closed cycle crafts, in millikelvin temperatures, in dilution refrigerators. But for tin vacancies, we don't really need to do that. I can have system operated at few Kelvin temperature without a problem. And also internal quantum efficiency of tin vacancies is larger, significantly larger than for silicon vacancy, which makes the atom brighter. And that's also, of course, preferable. But other than that, the energy level structure is exactly the same. Wavelength is different. You have to operate at a little bit shorter wavelengths. So you need a new experiment, new set of lasers, like in AMO, whenever you switch an atom, but everything else is exactly the same. So that's what we work on. And I'd like just to give one slide kind of overview of state of the art in silicon vacancies and tin vacancies, and then say a few words about the materials issues that I mentioned before. So with silicon vacancies in diamond for 5 or more years, people have been working on embedding them in structures, variety of experiments. Excellent photonic interfaces have been demonstrated by quite a few groups, including groups at Harvard and our team at Stanford. It's much simpler, as I mentioned, to embed it into a cavity and show strong, large cooperativity, strong Purcell enhancement than for example, nitrogen vacancy in diamond. And also recently at Harvard, they have demonstrated basically interaction, entanglement between two atoms, two silicon vacancies inside of the same diamond cavity. And they use magnetic field to tune them onto resonance with the cavity. So they've shown super radiance and interaction of two qubits. Of course, that particular platform is not exactly scalable because they use magnetic field around the resonator, and it worked in that particular case, but it could not really work in arbitrary case. But I'll show you some of the other ideas that we and others are pursuing to scale this to a larger number of emitters. And then with tin vacancies, in recent work, both in collaboration between Dirk England's group at MIT and Mette Ataturre at Cambridge, and also our recent work, we did a spectroscopy of the system. We've shown exactly that the energy level structure should look like theoretically predicted. So this is a very recent work. I mean, this new color center has emerged over the past couple of years. We've shown that we have very narrow line width of the transitions, even when we embed them in the structures, which is actually a very important ingredient for moving forward with this particular color center. And we have also very recently, a couple of months ago, demonstrated that we can even build optical structures, not just pillars to isolate single color centers, but actual optical devices around tin vacancies in diamond. And we can preserve very small line widths of about 30 megahertz, which is comparable to line widths inside of the bulk materials. So that's quite exciting. And we're kind of scaling this up to more complex photonic structures and more color centers at the moment. So going back a few slides, I said that with these systems, there are all these great advantages. You have already excellent photonic interface. Everything is much smaller. You're working with, semiconductors, and diamond is also considered a wide bandgap semiconductor. You can kind of use standard processing. All of that is really nice and really attractive, and you don't need quantum transduction. But there are a lot of problems that you have to deal with, first, you have to work with non-traditional fabrication approaches because everything is so small, and then you have to put this atom at the desired position at a regular matrix and do it in such a way that you don't damage the lattice. And when you look at all of these experiments, I mean, in principle, they should be immune. All these inversion symmetric color centers should be immune to electric field, static electric field. But then what happens in the experiments that they're not exactly immune to it, because you damage the lattice. You kind of break the inversion symmetry in the process of introducing these atoms into the lattice. And for that reason, in collaboration with groups of Nick Milosh and Ziek Shen at Stanford, who are focusing on materials and condensed matter physics, we have developed a new method on incorporating these artificial atoms into diamond in such a way that we don't really damage the lattice. And this process is named shallow ion implantation and subsequent diamond overgrowth. We call it SIG for short as an acronym. And the idea is pretty simple, right? We know that the main problem with incorporation of atoms into diamond is that you have to use a very high energy in order to push this atom or ion inside of the diamond lattice. And in that process, when you use ion implantation or focused ion beam, you damage diamond lattice and break inversion symmetry. And that additional strain kind of affects the properties of the environment and your atom. And you can change the transition frequency because of the strain, and you also have sensitivity to electric field. You increase line widths and so on. So that kind of damages everything that is favorable for that particular system. So to eliminate that, what we do is we instead implant our atoms at low ion implantation energies. So we bring it down from 370 kiloelectron volts to 1 kiloelectron volt. And we start with high purity diamond. And there are two things that happen in the process. First one is you don't damage the lattice anymore because you use very low energy ions. And the second actually advantage is that for 1 kiloelectron volt acceleration, you can use very simple masks consisting of the resist. So this is just a very simple ZEP mask or other resist that you use for your e-beam lithography. And that mask could resist 1 kiloelectron volt ions, meaning that you would only perform implantation at the desired positions. That's not something that you can use for very high acceleration energies because this mask would simply not prohibit highly accelerated ions from entering everywhere inside of diamond. So you will have them randomly positioned in the structures. And that has been a big issue in the previous experiments. So of course, when you implant them at low energies, they're just very close to the surface. And that's not something that you would like to have in practical devices. You don't want to suffer any effects from surface interactions. So what we do at the very end of the process, after we do ion implantation at desired positions, we actually grow using CVD, chemical vapor deposition. We grow synthetic diamond of high purity to cap everything. And that way we end up with these ions in the middle of some membrane eventually that is less than 200 nanometers thick. And here you see a regular array of these implanted tin atoms into the structure. Again, because of the reduction in lattice damage, you eliminate some spurious peaks that are occurring in the spectra that are not even related to tin vacancies. And also line widths of the transitions are much narrower and comparable to kind of naturally occurring tin atoms inside of the diamond lattice. So you are kind of getting closer to the best experiments and best line widths that are measured that way. We also work with silicon vacancy in silicon carbide, 4H polytype of silicon carbide. This is something that I mentioned at the very beginning. There's several types of silicon carbide that have different lattice. We focus on 4H, and in this particular polytype, there is also a number of different color centers that various groups are working with. And we are primarily focusing on silicon vacancy in silicon carbide. And this is essentially just a missing silicon atom inside of a lattice of silicon carbide. And since there are different symmetries of the spots where you can have a missing silicon atom, that's why you have different transitions that we refer to as V1 or V2. They're both in the range around 900 nanometers, so a little bit longer wavelength. And for those of us who used to work on indium arsenide, gallium arsenide quantum dots for many years, this is a great range to work with because that's exactly where indium arsenide quantum dots are as well. So we can actually use all of the experimental infrastructure. This is the energy level structure of this system. And I should mention that we've been collaborating very closely with the group of Jörg Rastrup in Stuttgart on all of these experiments, and also with Sofia Economou from Virginia Tech on the theory of this system. People have measured electron spin coherence time for silicon vacancy of 20 milliseconds. Generation of indistinguishable photons has been also demonstrated in Stuttgart by our collaborators. And transitions are very narrow and close to lifetime limit. And we also demonstrated that these car centers have extremely good stability. I mean, here you see transitions over 5-hour timescales, but we have measured this over even 10 hours or more. So they're very stable, and they have excellent limits and excellent coherence properties. There are other types of color centers in silicon carbide that people are studying, in particular in 4H silicon carbide. For example, there is a lot of activity at the University of Chicago in the group of David Avshalom on dye vacancy dye vacancy in silicon carbide, which is at a different wavelength. And there are some other impurities that are also being studied. There is a lot of exciting work, and actually silicon carbide is also interesting for the reasons that I mentioned earlier on, because it's more or less a traditional electronics material. So there is a lot of infrastructure there that we can use. It's simpler to process than diamond. So now, I gave this introduction into all of these quantum emitters and qubits that we're interested in. So the question is now, why didn't we scale it as much as atomic physics platform has been scaled or superconducting platform has been scaled? And the problem is in these inhomogeneities. I mentioned that we've done a lot of work, and of course others have also done a lot of work on trying to minimize damage to the lattice and to the structure when you are implanting all of these artificial atoms and where you are incorporating them at the regular positions, but there are still some inhomogeneities. So when you look even results of our shallow ion implantation and overgrowth, of course yield is never 100%. But you see a regular array, but some spots are empty. It may also happen that you have 2 atoms at one spot or no atoms at some spots. So there are those types of spatial inhomogeneities that you have to deal with. And also there are spectral inhomogeneities. So this here is for silicon vacancy, but thin vacancy is very similar. So these are transitions of silicon vacancy, which are around 740 nanometers. And there are these 4 lines in the spectrum. So when you measure it for a single silicon vacancy, you would see a red spectrum. And then when you measure it for an ensemble of silicon vacancies for the same chip, exactly from the same chip, then you would see the black spectrum, which means that there is some homogeneous broadening. And we have measured 30 gigahertz of inhomogeneous broadening, which is much, much smaller than for indium arsenide, gallium arsenide quantum dots, where you have to deal with 50, 60 nanometers of inhomogeneous broadening. But still it's something that you have to resolve before you can scale systems up. And the reason why we have this inhomogeneous broadening is, again, imperfection of the crystalline structure that surrounds emitters, that surrounds qubits, which basically breaks the symmetry, affects their transitions, or makes them affected by the external electric fields. And these inhomogeneities are something, again, that we have to resolve and address before we can scale systems up. So we worked on a variety of methods for tuning these color centers onto each other that would also work for different color centers on the same chip. And for diamond color centers, here I'm showing the result for silicon vacancies, but of course this works also for thin vacancies. We have developed cavity enhanced Raman scattering from a single silicon vacancy. And this is the work done by my former postdoc, Shuo Sun, who is now at Gila in Boulder, starting his own group. And the idea here is that in order to compensate for the inhomogeneous broadening, you can drive your color center off resonantly with a laser. You can change the tuning from the excited state transition and then perform Raman scattering into some optical mode. And by tuning your driving laser, by changing the tuning of your driving laser, you can also change the frequency of the Raman scattered photon. And of course, for atomic physicists, this is nothing new. I mean, this is type of excitation that is performed on lambda systems all the time. But we have done it for color centers inside of the cavities. And you see that you can tune the frequency of the scattered photon, but the most important part is that you can tune it by up to 100 gigahertz. And as I mentioned previously, we have shown that we can grow color centers with 30 gigahertz inhomogeneous broadening, which means that by this technique, you can compensate for all of the inhomogeneous broadening between color centers. Of course, the price you pay is you have to drive them with separate lasers, but you can interact scattered photons that are the same frequencies. Later on in the talk, I'll show you the ideas that we are pursuing in order to simplify this so that you don't really have to drive each atom with a different laser, which of course at some point becomes prohibitive because you need hundreds or thousands of lasers for your experiment. So that's one method that we pursue for diamond. And then for silicon carbide, we've shown that we can use DC stark shift. So we just put electrodes next to the color center and apply voltage, and then we can tune color center by a few hundred gigahertz. Again, we can compensate for all of the inhomogeneous broadening of the system. And in the process, we're actually not affecting properties of the lines. Line width is small and stability is still pretty good. So here, the approach is different. You have to put electrodes and apply voltage electric field in order to actually tune the color center itself. But again, with this approach, it would mean that you have to essentially apply different electrodes to different color centers, which is why we started thinking about doing something more scalable, right? Instead of just DC stark shift. I mean, we know that we can compensate for all of the inhomogeneous broadening and all of the inhomogeneities, but the question is, how do we do things that are kind of smarter in order to reduce the complexity of the system instead of putting a separate electrode or separate laser for each color center in the system. So very recently, we started looking into ideas of flow K engineering, which again, of course, is something that has been done quite a lot in atomic physics and superconducting systems. Here is kind of one step beyond just applying static electric field or Raman driving, because we're looking into the idea of optimizing modulated drive on the color center in order to produce the desired spectrum at the output. And at this first step, we've still looked into driving each color center with a different modulated drive. But again, later on in the talk, I'll show you our ideas, how we can actually simplify that further. And again, the approach is pretty similar to what I showed you before, but instead of just applying static electric field and tuning everything on resonance, we just optimize the drive that we would like to have in order to produce a particular spectrum of the emitter at the output. And for that optimized drive, we can actually make also emitters which normally would not interact. We could make them interact through photonic structure or through interact with each other. So here are some of the experimental results that we have on that. So this is again on silicon carbide color centers, silicon vacancy in silicon carbide. When you apply periodic drive on a color center, you expect to see flow K eigenstates in the system, and that's theoretically predicted, and we observe it in the measurement. So you have this kind of spectrum of eigenstates that are occurring, and they depend on the drive frequency. And we also show from our second-order photocorrelation measurements that we actually indeed work with single color centers in these experiments. They're modulated, and the signature of modulation appears in the side bands of your second-order correlations. And I should mention that here we're talking about driving them with modulation frequencies which are larger than their decay rate. So we're talking about modulation at few gigahertz frequencies, while their decay rate here is on the order of a gigahertz or so. So these are just flow K eigenstates, but that's periodic driving, right? What we would like to do is not just simple periodic drive, but optimized drive, meaning that you start playing with microwave drive, and of course that could also be optical drive, right? Some modulation on the laser for case of Raman driving of color centers in diamond. But here we're talking about microwave drive, and we are kind of optimizing the driving signal in such a way that we produce particular spectrum at the output, beyond a simple spectrum of flow K eigenstates that you obtain for periodic driving. So if you start increasing these harmonics in the microwave drive beyond simple periodic drive, your spectrum at the output will also change. And you can go beyond like simple symmetric spectrum. You can actually produce something completely asymmetric by engineering engineering harmonics in your microwave drive, which we can find quite interesting, especially since we have a lot of inhomogeneities in the system, and then we can make this interesting spectra at the output that would overlap with each other. We've done that experimentally for color centers in silicon carbide. So here is a 2-color drive. Here is a theoretically predicted behavior of the system, and we measured it at 1.5 gigahertz drive frequency. And here is the experiment. And you see 4 peaks at the output. The 2 of them correspond to spin 3/2 manifold. The other 2 correspond to spin 1/2 manifold. When you change the drive to 4-color drive, I mean, you mean 4 harmonics in your microwave drive, then in your output spectrum, you will see 8 peaks. And again, normally you would see only 2 peaks, but here you see 8 peaks because you have 4 peaks that emerge from the spin 3/2 manifold and 4 peaks that emerge from the spin 1/2 manifold. And you can change the symmetry by kind of playing how much contribution you have in different harmonics. You can change the symmetry of the spectrum at the output and make it look very different from this one. And in addition to this, we have also shown that even when we drive system with a microwave modulation, and all of these experiments were performed on single color centers, single quantum emitters, we can also perform pulse optical coherent control of these modulated single emitters. We can actually use Ramsey driving pulse sequences in order to rotate the state of this quantum emitter anywhere on the Bloch sphere. This microwave driving is not really affecting the process. For some conditions, it's destructively interfering with the process, so you don't really need such a high contrast, but you are still able to actually put your qubit anywhere on the Bloch sphere. So that's kind of this first part of my talk, and I'll make a break after this slide to see if there are any questions. Before we make a break, I'd just like to prepare you for the next part of where I will like to talk more about the photonics part, because so far I focused on our qubits or these solid state quantum emitters, which we're working on in silicon carbide and diamond. But of course, that's not enough to build quantum simulators and quantum computers. We also need to have connections, optical connections between them. And that's what I would like to address in the second part of the talk. How do we make them and connect them in the most efficient way into something that is scalable? Okay.
Great. So I'll start by just reminding everyone to please feel free to enter questions either through the Q&A function in Zoom or through the chat function in YouTube. We do have some questions mostly from the panelists so far. So Dan Snipper-Kern was wondering, when you showed the table of the different properties of the different defects in diamond, for example, what makes the quantum efficiency of different color centers change so much?
Yeah, so for the quantum efficiency that is noted for different color centers, it's a multi-phonon process that to reduction of the quantum efficiency. And when you change the wavelength, I mean, when you implant a different color center transition, wavelength changes dramatically. So it is basically detuned from that multi-phonon process favorably, so that the internal quantum efficiency is larger. That's basically the hypothesis. And we do see that in tin. Again, these are very recent experiments. So this is all based, a lot of the results that are quoted there are actually not based on measurements. They're based on DFT calculations on the theory, but we do see that tin is brighter than silicon, which means that, again, as the spectroscopy also for the quantum efficiency, we do see agreement, but we didn't really measure it exactly.
Great. So Shuyu Zhang is wondering about, with the flow K engineering, do you run into problems with scalability with frequency crowding when scaling up? So is it possible, I mean, do you run into some of the same problems that you have with addressing each one with a different laser versus now you have?
I think that's an excellent question, and that basically prepares the discussion for the later part of the talk, where I will show you exactly what we're thinking about doing with this. So we don't really plan to do a separate drive for each emitter. In fact, the idea is to optimize drives so that you apply global drive to some number of emitters, which would be the same laser or the same set of electrodes. And we already have theoretical results which indicate that this is possible. What is the limit to the number of emitters that you can kind of control with the same global drive? We don't know yet, but this is something that we're working on actively at the moment. So I'll tell you that more about that towards the end of the talk. But so far, experimentally, we've only done experiments on individual quantum emitters and Fourier engineering of a single emitter spectrum.
Great. And maybe we'll do one more question. So Aziza actually was wondering, what are the cooperativities of a spin defect in a single optical photon in these structures that you're fabricating? And how do they compare to cavity QED systems with neutral atoms and circuit QED systems?
So the state of the art for thin vacancy, nobody has done measurements yet, and we're currently working on that, embedding them in the cavity. There have been no experiments demonstrating kind of cooperativity for thin vacancy yet. For silicon vacancy, the record value recently demonstrated at Harvard, again at milli-Kelvin temperature, is on the order of around 100. So it's comparable to atomic physics systems, but that was done at, again, in dilution refrigerator at milli-Kelvin temperature, because for silicon vacancy in diamond, you have very small ground state splitting. And in order to kind of prevent all of this mixing between ground states, people have to cool down the system to very low temperatures. We do expect that for thin vacancies, we should actually be able to achieve the same range of cooperativities and again, operate at kind of elevated temperatures. And also relative to systems with quantum dots, cavity QED platforms with quantum dots, again, this is getting to a comparable range to what we and others have demonstrated some number of years ago. Ultra strong coupling regime, for example, that circuit QED platform can be used to demonstrate, I think that's out of the question in these systems, because you basically always operate with lossy cavities, and your coupling strengths are not so large that you can kind of observe ultra strong coupling regime. You can observe strong coupling, but you are always operating in the regime where you have a bad cavity, basically.
Okay, great. I think we can probably go on for the and save the rest of the questions for the next break.
Okay, great. Thank you very much for the questions. And now let's kind of shift gears and talk a little bit more about the photonics, right? How do we connect these systems? And again, for all of the ideas that we're interested in pursuing, which include quantum simulators, containing optically interconnected spins on the semiconductor chips, or quantum networks where you connect them over long distances, we actually need some photonic connections, right? Of course, you always need some connections. Even in superconducting systems, you need microwave connections, right? But for us, the connection channel are photons, and we would like to do that efficiently so that we don't really lose photons to a variety of losses in the system. And in order to do this efficiently, we are relying on inverse design, photonics inverse design that we have pioneered some number of years ago. And this approach allows us to kind of search the whole parameter space of fabricable structures for a particular function and design and implement devices that are robust and insensitive to a variety of errors. So here are silicon devices that split different colors. And this is for 2 channels, this is for 3 channels. This is a result of this optimization that we apply. And here is the measurement for these devices. And you see here superimposed measurements for many different devices on the chip. And although our fabrication is not perfect, they all look the same because we designed them to be robust to typical fabrication errors that we have. So as opposed to traditional approaches in photonics, where you need to tune every single element of your photonic integrated circuit with some tuning element like heater or some MEMS component, we don't need to do that. We just simply design them to be robust to typical errors that we have in the process. And we developed this software suite, which we call SPINS, Stanford Photonics Inverse Design Software, that now several companies and research groups are also using. But we also have a basic version open source of this software on GitHub, which we call SPINS-B. So if you're interested in playing with this, you can download it, or also, you can also use our full version. If you're interested, you can get it from the Stanford licensing office. So what are we doing here? Well, the main idea is combining typical classical optimization techniques, kind of gradient descent, but in this complex parameter space, with fast electromagnetic solvers, and then we search all the parameter space to find the right solution. So here is, for example, how optimization of the mode converter would look like. You're converting first order mode to second order mode in a very small footprint, like 2 by 1 micron, much smaller than a diabatic mode converter that people would typically use in photonics. And you see that this works at the end of this first phase, but this is not something you can make because you have continuous change of the refractive index. And then in the second phase of this process, we do binary optimization, where you make something that you can fabricate, and you see that your device at the end actually also performs mode conversion. And we stop when we reach the target efficiency for the function. And I should also say that all these are three-dimensional optimizations of the full parameter space, but I'm just showing a crosscut. We constrain the pattern to two-dimensional pattern because that's something that we can easily fabricate, but vertically it's kind of a slab of silicon on insulator here. And we spent a long time also developing fast electromagnetic solvers for this. So full optimization of something of this size would take about 1 hour on gaming GPUs. So we run it on gaming GPUs, not really scientific grade GPUs. And that would take around 400 iterations, which is on the order of about 1,000 electromagnetic simulations. And you can already see that this is faster than commercial electromagnetic solvers because you can run 1,000 successive simulations within an hour on kind of gaming platform. So this is not the topic of this talk, but we've done a lot of work on a variety of other things. Apart from these wavelength splitting devices, we've also demonstrated stages of one single stage of a laser-driven particle accelerator. We've accelerated electrons with something like 30 mega electron volt per meter gradient, and we're cascading these stages to build mega electron volt accelerator. We've shown some non-reciprocal pulse routers, which are useful for ranging measurements. And we've also shown that this is fully compatible with foundry-based fabrication, as I'll show you in a moment. And this approach is completely agnostic relative to the platform. So you can actually run it on whatever material you would like to run it on: silicon, diamond, silicon carbide, lithium niobate, whatever your material of choice is. You just need to know your fabrication constraints and properties of the material. So for foundries, which primarily work with silicon, we've also spent the last couple of years showing that you can actually do this in a foundry. So for example, the 3-channel wavelength splitter we fabricated at Stanford and demonstrated. Here is the same splitter made in a commercial foundry. Here is the theoretically predicted behavior, transmission into 3 different channels, and here is the measured behavior for many devices on the chip. Again, they're robust to fabrication errors, and small degradation relative to theoretically predicted behavior comes from the fact that we didn't really know precisely minimum feature sizes in a foundry. They were around 100 nanometers, and we designed this for minimum feature size of 80 nanometers. So now going back to quantum optics and the work that we do, we can apply this approach to diamond and silicon carbide. Here you see a variety of interestingly looking devices that we designed and fabricated in diamond. They significantly improve behavior of the device without increasing the footprint. For example, the simplest function would be coupler, vertical coupler in the direction perpendicular to chip, free space coupler. We can design it to be much better than these notch couplers that couple only 1 to 2% light that people often use. And with the experiment, we can reduce experimental time. Instead of barely seeing a signal after you integrate for 10 seconds, after a single second, you see strong cavity signal. So you can kind of start thinking about scaling this up because you're not really limited by experimental times and signal to noise ratios. And of course, it's all about efficiencies. We're collecting many more photons in the system. And we're also applying this to silicon carbide. And I'd just like to spend a moment kind of saying a few words about silicon carbide, which is a very interesting material apart from quantum optics. Of course, it hosts very high quality quantum emitters, but people also use it in electronics for power electronics applications. So it's available on wafer scale. It's silicon compatible. You can in principle use silicon foundry to process silicon carbide as well. It has excellent thermal conductivity, large band gap, it's piezoelectric, and it has strong optical nonlinearity, including second-order optical nonlinearity like lithium niobate. In fact, not very different from lithium niobate, a little bit smaller, but photonics is simpler to fabricate and process, so you have higher quality structures, which compensates for a little reduction in bulk nonlinearity. So just before I tell you about our work on silicon carbide photonics, I'd like to just kind of give a little bit of historical overview of various photonics platforms. Most of the people really work on silicon photonics, and that started about 20 years ago when companies commercialized silicon on insulator wafers, because you always need some guiding layer in order to build photonics. And that was about 40 years after bulk silicon wafers were commercialized. And then the last 10 years, people have been working actively on thin film lithium niobate. That was, again, when it was commercialized, and that was, again, 20 years after bulk lithium niobate was commercialized. And as of last year, when we started actively working on silicon carbide photonics, there was no commercial silicon carbide on insulator, although it's been a long time, 30 years since bulk silicon carbide was commercialized, and you can get it even on 6-inch wafers, and it's much cheaper than diamond. So we had to come up with a process to make thin film silicon carbide on insulator, and we just start with silicon carbide wafers. We bond them onto oxidized silicon and then grind, thin, and then do fine tinning, and that way we end up with chips that are pretty uniform, and we can make a lot of photonics within these several millimeters, but we can also scale this up to larger wafers if needed, although that's not something that we need for our own fabrication. And this process, which looks kind of quite simple, is crucial for enabling these high purity, pristine films of silicon carbide on insulator. If you try to repeat the same process that people use to make silicon on insulator, which is so-called smart cut process with ion implantation and lifting off films and transferring, and we spent 2 years doing that, it doesn't work because you have to bombard with ions, and that introduces unintentional defects, or it kind of affects the structure and degrades it for quantum optics. And as a result of this very high quality silicon carbide, we're now able to measure really high Q factors, actually better than in silicon on insulator. We have Q factors of 5 million, very low loss. This loss is comparable to based silicon nitride. We can combine it with inverse design, and there are a lot of structures that are shown here. See some of the older measurements with Q of 1 million. Again, you see inverse design couplers. We use them routinely for this. And this is silicon carbide sitting on insulator, but you can also remove insulator if you would like to have kind of suspended structures. So once you make silicon carbide on insulator, basically fabrication is the same as dealing with silicon photonics. We've also demonstrated nonlinear optics. There is a strong second order optical nonlinearity. Initially, we demonstrated second harmonic generation with efficiency of 360% per watt, but that was at a time when Q factors of resonators were smaller by a factor of 10 or more. So now we actually should be able to measure this with much higher efficiency because it scales as Q factors squared. And also, very recently, we demonstrated optical parametric oscillation with low thresholds, or 8 milliwatt thresholds, and then at higher pump powers, you see microcombs. So this is, again, employing nonlinearity, optical nonlinearity in silicon carbide, so you can actually even scale this up to stable soliton frequency combs. So this is a very recent measurement from a few weeks ago that we made, and we can demonstrate soliton. This is a stable soliton frequency comb on silicon carbide chip with very low threshold. And of course, this is due to strong nonlinearity and also high quality of the structure that we demonstrate. This on its own has a lot of interesting potential application in metrology, but also in kind of quantum photonics that even doesn't involve quantum emitters. But I am showing it here, although our primary interest is in using optically interfaced spin qubits. I'm showing this because it tells you that the quality of photonics is extremely good, and that you can actually use this platform also to do quantum frequency conversion right away, right? If you would like to interface your emitter to fiber optic network, you don't need additional materials. You can do everything inside of silicon carbide, converted from 900 nanometers to 1.5 microns. And On top of everything, I mean, in the process of producing silicon carbide and insulator, we don't really degrade color centers. They have excellent properties. We can couple them to cavities, and we've shown strong enhancement of their emission on cavity resonance by a factor greater than 100, reduction of radiative lifetime, and we've also measured basically photon statistics. So we're now going in the direction of kind of scaling this, connecting different quantum emitters. In any platforms that you work with, there are always imperfections and there is always imperfect yield, which means that you need some level of reconfigurability. I mean, this is what you do with optical tweezers for atoms, or in superconducting qubits, you also need to rewire, reconfigure circuit to bypass kind of non-functional qubits, right? We need to do the same. And in silicon carbide, that will be relatively simple because you can add another layer of lithography to connect kind of good working, kind of good qubits that you identify in your system. And that could be done, for example, in a layer of silicon nitride. And then you don't really need any other materials for your quantum frequency conversion or interfacing for fiber to fiber optic network. And of course, on top of this reconfigurability, you also have this electrical reconfigurability that I was talking about previously, where you can apply electrical signal, either optimize periodic driving or just DC stark shift in order to reconfigure your network. So now maybe I should check if there are any questions before I move on to Outlook, or if there are no questions, I can keep talking.
We do have a couple of questions, so maybe we can take it quickly. So Ivan Deutsch was actually wondering, for the inverse design optimization, is it known that the landscape you're exploring is favorable? Do you get stuck in suboptimal traps, and how hard is the optimization?
Yes, so this is an excellent question. This is a local optimization, not a global optimization algorithm. It's based on essentially gradient descent, multidimensional gradient descent. And you never know if you are in a global optimum, but that doesn't matter as long as you are in a local optimum that satisfies your figure of merit, which is particular input to output mapping and particular efficiency. And also we run constraint optimization, which means there are minimum feature sizes and a lot of other things that we incorporate. Having that said, we probed this problem for a variety of different initial conditions, and even for these wavelength splitters that are much more compact than traditional solutions, we found, for example, 6 solutions with the same efficiencies in the same footprint, which means that everything that we work with in photonics is highly suboptimal. There are a lot of better solutions that are more robust to errors and have smaller footprint. Landscape depends on the function. So when you change the function, go to a different device, landscape can be completely different. And we're also working on the problem of bounds for inverse design, which means, what is the minimum footprint that you need to start with to get a particular efficiency, or in other words, I mean, that those bounds on these problems would tell you how the landscape, maybe more about the landscape before you even start running optimization. So it's not a trial and error. So now there is a trial and error, but we made it fast, so you don't really need to wait a long time to get a feedback. You have a feedback after about 10 or 15 minutes, and you know whether you need to restart it and reinitialize to get into a different solution.
Great. And then Connor G, I think, sort of asked right at the end of the previous question session, is there any research on implanting rare earth ions in diamond silicon carbide?
Yes, there is work by Tian Zhong and University of Chicago actually on putting some, I think, rare earth ions inside of silicon carbide. And there is certainly interest. I mean, most of the effort still is on silicon vacancies and silicon die vacancies, but people have worked on also a variety of other impurities. I mean, this field is, like for diamond, very rich. People are looking for the ideal atom to do their experiments. But for now, the most understood and studied are silicon vacancies. Okay.
Great. Okay. I think we can probably move on to the outlook. Yeah.
Yes. So now actually let me spend a little bit of time talking about Outlook and what we're actually really doing now. And I said we want to build the quantum simulators on the chip eventually, or quantum networks relying on these systems. And for quantum simulators, we're looking into ideas. Some of the ideas that have been proposed by a group of Ignatius Chirac and Jeff Kimball some time ago, where the idea is to couple arrays of atoms to optical structures underneath, and then use optical density of states or properties of the optical structures to mediate the interaction between atoms. And it turns out that by changing dispersion of the optical structure, by changing the density of optical states, you can control the range of interaction between the atoms inside of the Hamiltonian. Jeff Kimball's group has tried to perform these experiments for some number of years. But with atoms, I mean, it's kind of quite hard to couple atomic array to photonic structure underneath something like photonic crystal that has periodicity of a few hundred nanometers. And we think that technologically, this may be simpler to implement in our solid state platform. I mean, because our atoms are naturally trapped, there will be some empty spots, but we of course have to deal with inhomogeneities. And I'll tell you in a moment how we plan to deal with that. But before I tell you about it, I would like to also say that using inverse design, we can also do a lot of sophisticated dispersion engineering. And this is related, of course, to problems in nonlinear optics, but also in problems in quantum simulation, in particular related to the proposal that I showed on the previous slide. So for example, if you try to manually achieve some dispersion, and dispersion is omega versus k wave vector relation for photons in a structure, and if you say, I'd like to have this kind of very slow group velocity inside of this photonic crystal waveguide, whose one period is shown here, manually, you'll never really be able to do that. At best, you can get something like a black line here. But if you do optimization, you can hit design target pretty well. So here is optimized structure, one period, you have to kind of cascade this in space, and you have a large group index in a pretty large bandwidth. So this beats everything that has been manually designed. And you can also do microresonator dispersion by inserting some dispersion compensators that are introducing frequency dependent phase shift. And we're doing this in the context of frequency combs to engineer the spectrum of the frequency comb, but it's again a dispersion engineering problem. So we know how to engineer optical density of states pretty well, but now, I mean, if you think about simulators, what about atom, right? There are all these inhomogeneities still that you have to deal with. So one option is, oh, well, I can drive them with separate lasers or separate set of electrodes, but that's pretty hard, right? And of course, when maybe you can go to 10 or maybe 20 that way, but how do you scale to 100 or more? So we started thinking whether it's possible to do something better. I mean, can you, instead of applying separate electrodes to each of these 10 emitters inside of this optical structure, can you have something like a single global drive, one set of electrodes or one single modulated laser that drives all of them and makes them talk to each other despite inhomogeneities in the system? And this kind of resembles the problems that we're solving in photonic inverse design. So we call it inverse design of quantum systems or quantum inverse design. Just to remind you, in photonics inverse design, all that we're doing is we're coupling fast electromagnetic simulator with some fast optimizer, and we're starting from some kind of footprint and some target performance, and then searching the whole parameter space by kind of going back and forth between simulation and optimization until we obtain something that does what we wanted to do. In quantum inverse design, and this is the work led by my student Raul Trivedi, who just graduated yesterday, the idea is to couple some open quantum system simulator with an optimizer. An optimizer is, again, some gradient descent algorithm, similar to the ones that we're using for photonic inverse design. And can we actually use this, like we do in photonics inverse design, to kind of optimize geometry of some quantum system in such a way that we obtain at the output performance that we want, right? So can we obtain Hamiltonian, or can we obtain some quantum state at the output that does what we want it to do, right? And of course, there are a lot of different problems for which you can optimize. It's not exactly just a structured geometry. We also optimize geometry using photonics inverse design, but I'll show you some examples of things that we've done so far, which make us believe that this is actually possible and that this could be used to simplify all of these other tools that we use in order to reduce inhomogeneities in the system. And of course, this is not applicable only to systems that we work with, it's applicable to all the other quantum systems as well. So here is one example. We looked into a problem of quantum transduction. Quantum transduction, of course, is the problem that many groups work on. The idea is to transduce the state of a microwave photon to an optical photon. And there's very nice proposals, and many groups are working on the idea of using ensembles of solid state emitters driven by the microwave and optical signal. And that way you obtain at the output, you transduce the microwave state into an optical state. But the problem is that whenever you take this solid state ensemble, there is some inhomogeneity, right? Not all of these atoms are the same. And then that collection of emitters has some inhomogeneous broadening, and that affects your transduction efficiency, right? Because all the transitions are all over the place. So we wanted to look into the problem of kind of optimizing laser driving, for this system. And normally in the transduction experiments, you don't optimize laser drive. You kind of drive it with CW or pulsed laser, but you don't worry about what you drive it with. We want to optimize laser drive or microwave drive in such a way that we overcome inhomogeneity here. And this is the work done by my students Satvik Mishra and Raul Trivedi. The idea here is to kind of find the optimal drive in order to minimize that inhomogeneity. And here are some of the results that we've done, and we've done it over kind of various random distributions of atoms inside of the ensemble and for different cooperativities in the system. And as you see here, you can actually improve transduction efficiency significantly, on average by maybe a factor of 10, but in some cases by a factor of 20, just by optimizing the drive that you apply on the system. And of course, drive would be different for different ensemble of emitters. So you have to do spectroscopy and see how your ensemble looks like, and then optimize drive for that case. But then we also have some results on where we don't really optimize it for a specific ensemble. We just know what the kind of on average ensemble would look like, and we optimize the drive for that, and it still leads to some improvement, not the maximum improvement, but it leads to average improvement. So here is, again, one problem where very simple optimization can help you significantly affect the properties of the system. Then the other problem we looked into is a problem of multi-emitter cavity QED. And here also my student Alex worked on this problem with Raul. What is a multi-emitter cavity QED? Again, I told you that the state of the art for cavity QED with silicon vacancies in diamond is coupling of two atoms to the same cavity at Harvard, but people were fortunate that they could actually tune these two detuned emitters onto the cavity resonance by the external magnetic field. So we were interested whether if you have 3 or more atoms and they're different from each other, they're detuned from each other, can you couple them to the same cavity by doing some sort of optimized drive on them? Of course, if you don't do anything, if you measure transmission, you'll just see separate peaks for atoms and you see cavity resonance. There is no really strong coupling, right? But then if you drive them with microwave drive, and again, this is exactly the same as the configuration that we use for flow K engineering. You have one set of electrodes, you have 3 atoms, 3 silicon carbide atoms inside of the cavity. You optimize the microwave drive in some way to produce this collective coupling. And indeed, this is still a theoretical result, but at least in theory, we know that we can recover strong coupling. And what is really happening is that this optimized drive is producing some flow K eigenstates on all of the emitters, and they end up overlapping and interacting so that they produce basically this collective coupling at the output. Again, this is much simpler than putting 3 different electrodes on each emitter, which it wouldn't even be possible for sizes of the cavities that we normally work with. And one last problem is designing entanglement in emitted photons for modulated quantum systems. This is building up on some ideas we did in the past, where you're just driving a quantum dot with a laser pulse, and you can produce 2 photon state at the output as a result of the re-excitation of the same emitter. But now we're also applying microwave drive on the same system, and we're interested whether we can produce a particular 2 photon state at the output with particular presence of one frequency versus the other, particular entangled state. And we've shown that we indeed, just by adding this microwave drive on the same system, we can control the spectrum at the output and basically with pretty high fidelity produce desired photon state. Again, in theory, but we're planning to work on this in the experiments. So now let me just wrap up by saying that I really believe that some of these semiconductor platforms will be scaled up to larger systems, not too far in the future, but we have to rely on a lot of also optimization techniques and of course novel fabrication techniques. But I think the optimization of both photonic structure and optimization of the drive on the system beyond like simple optimization and pulse sequences that we normally do in quantum experiments would enable actually much easier scaling. And this is what we're actively working on right now, as you saw at the very end of the talk. And let me thank my group. This is from a little bit over like maybe around 9 months ago when we could take a picture outside of the building. I already acknowledged collaborators, but for the work that I presented today, primary contributors were Raul Trivedi, Alex White, Shumon, he is now in Boulder, Alison Ruger, who works on diamond, Satvik, who works on quantum transduction theory, Konstantin, who graduated, he worked also on diamond, and Melissa and Daniil, who work actively on silicon carbide, and also Kyo here, who also works on silicon carbide. And thank you very much for your attention. Thanks.
So thanks, Jelena, for a really excellent talk. Really exciting. So actually, we haven't gotten too many questions during the Outlook section of your talk, but you know, we asked for a number of questions during the talk. There was one question from Aziza from earlier, actually. Are there prospects of coupling spin defects in solid state to millimeter wave photons to use as qubits, so 30 to 300 gigahertz, for example?
Yes, that's a good question. Actually, I mean, there are transitions in that range. So in principle, you could couple them by driving directly some of these transitions. And you're talking about the quantum transduction problem, or basically primarily in the context of quantum transduction, or coupling to microwave photons, driving some of the transitions with millimeter waves, right? Or yeah, definitely there's some you know, favorable transitions where you could do that, but we haven't really looked into that. I mean, some groups are thinking into that direction, primarily again in the context of quantum transduction. What we're primarily working on is all optical control of spin qubits. And the reason, I mean, people have done microwave control of spin states in a variety of these systems. We think that all optical, fast all optical control is possible. And that's where we collaborate with Sofia Economou. And this is related to something that we and others did on quantum dots in the past, because you can actually do spin rotations with very short pulses, all optical pulses, with a single pulse, for example. And you can do that for quantum dots with tens of gigahertz speed in principle, with very, very short optical pulses, which means that within the electron spin coherence time of your system, you can do a lot of spin rotations. You can actually do very fast operations. So that's the primary reason why we're kind of thinking in that direction and focusing right now on all optical spin control. And but certainly there are other ideas. Some people are actually looking into coupling them to also mechanical vibrations. I mean, there is a work at Harvard on interfacing them to phonons, and you can certainly couple them to microwave or millimeter waves. And there is a lot more to be done. I mean, some of these systems are pretty new and relatively recent.
So Monica asks, when using optimized driving to combat inhomogeneous broadening, presumably you add some sidebands that do couple to the cavity and others that do not. Does this mean that the effective cooperativity for a single emitter is reduced? How does this scale with the number of emitters?
Yeah, that's an excellent question. So for the cavity QED system, we've done it only for 3 emitters. I mean, so I don't have the answer to how this would scale. And I think it would actually certainly depend on the statistical distribution of your emitters. I mean, again, you have to keep in mind that what we're doing is we're driving it with some optimized drive. So if you are producing some sidebands in your spectrum of each of your emitters, right? And in order to make them interact, you have to produce sidebands in the bandwidth that is kind of as large as your inhomogeneous broadening, right? Which means that you have to drive them also with the frequencies that are kind of comparable to that inhomogeneous broadening in order for this to work, right? And for us, I said we work with kind of bad cavity regime. Our cavities are generally broader than, or kind of comparable to our, on the same order of magnitude as inhomogeneous broadening. I mean, not exactly the same, but they are somewhere there because we like to work with low cavities. So I think our system is different from the system that you would work with in atomic physics, where you have ultra high Q cavity, right? So that we don't really, for the system of 3 emitters, at least we managed to recover collective coupling to the cavity, right? Because kind of everything was, again, lossy and on the same scale. But for a larger number of emitters, or for different emitters in ultra high Q regime, Q cavity regime, I'm not exactly sure how far we can go. It's an excellent question, and these are relatively new results that we're looking into. So I'd like to talk more and to see whether we could also help atomic systems in this way. For quantum transduction problems, we worked with few dozens of qubits, and we actually assumed cavity properties that are kind of state-of-the-art cavity properties in diamond. And we have seen at best something like 20-fold improvement, which again comes from the fact that, you know, they are coupling kind of to the same resonance and interacting with each other. But, you know, clearly, since you're forming side bands and not everything will be coupling to the cavity, there will be some inefficiencies or some loss, but I don't have a number to characterize this yet. And I think it would be heavily system dependent, depend on the cavity line width.
Okay, let's see. So we had a couple more questions that I suddenly lost. Here we go. Okay, so Shuyu Zhang asks, thanks for the excellent talk. Does the spin software also apply to the microwave domain? Can you also use it in the microwave domain?
Yeah, definitely. I mean, as long as you know properties of your material at the frequencies at which, I mean, it's basically just Maxwell's equations, right? So it's a fast electromagnetic solver, in frequency domain solver, but we've interfaced it to other types of solvers. So you need to know properties of your material at the frequencies that you're probing, like refractive index. You can insert a loss as well, although typically for dielectrics, we don't really have loss. We just have real part of the electric constant. But other than that, kind of like electromagnetic solvers, everything is scaled relative to wavelength, right? So all of these kind of pixel sizes, which are for us variable pixel sizes, but it doesn't matter, are kind of related to wavelength, right? So if you're doing some dielectric material at microwave frequencies, for you, everything would be just scaled up, right? And also depend on the refractive index that you are using. One note there is that if you're interested in doing something like plasmonic modes and so on, you run into the same issues as you normally have with electromagnetic solvers, that if penetration depth is very small, then you have to do very fine discretization inside of the structure. So electromagnetic simulations become pretty large. So you may run into problems of, you know, having to run much larger matrices that we're normally solving. But if you're thinking about some dielectric materials, then it's going to be the same complexity as the problems that we're solving.
Okay, maybe we'll end with a sort of a grand vision question from Dan Stemper-Kern. So Dan says, there is a lot of interest nationwide in an intensified interaction between science, engineering, and industrial R&D to develop quantum technologies. What would be a really big advance that could be achieved by this interaction in the optical technologies you are developing that a 10 to 20 year deep investment could achieve?
That's a really deep question, and then to answer in a minute. Well, I should say that a lot of things that have been developed in the process of scaling, not just photonic technologies, but all quantum technologies, have also been important for other fields, not just of research, but also in case of photonics, other practical fields, right? So inverse design, for example, which was primarily motivated by our attempt to reduce losses in our quantum photonic systems, kind of led to a lot of interesting applications in classical photonics, right? So now there is a lot of support for that from classical photonics community, because it's opening new opportunities there. So I would not look into these developments separate from some industrial efforts that are maybe not directly related to quantum, because even for atomic physics, of course, there is a lot of industrial interest and efforts related towards developing new lasers and high-speed switches and integrated photonics for control of atomic systems, and there is a lot going on that is not necessarily quantum, but could enable things both in quantum and in classical direction. So what are things that could make our lives easier? I guess that's the other part of the question. we work with new materials and we've identified some excellent materials, but photonics is still silicon, world, right? And, all of the industry, both electronics industry and photonics industry is primarily focused on silicon, right? So there are no really foundries, major foundries that could process some of the more exotic materials that we and others are working with. And that even includes silicon carbide, which is a fully compatible silicon material. Nobody has set up a foundry, right, to make silicon carbide chips and wafers, and a combination of electronic and photonic devices there. And also there is no provider of high quality thin film silicon carbide wafers. We make them ourselves, the highest quality ones. Now there is some industrial effort, but using different process because they're primarily driven by automotive applications. So I think for in the industry, of course, is pretty conservative, right? I mean, when they, what I know from classical photonics or from electronics, being in electrical engineering department, is they don't really go into something unless they know that would be, that people, would want it 5 years from now. And they're driven by things like automotive industry, or sensors, or things that have clear applications five years from now. But quantum technologies are probably not as clear as the applications in other areas, which is why I think we have to rely on government funding to develop a lot of new technologies until industry becomes convinced that it's worth investing into a foundry for this material, or it's worth investing into developing wafers in a new material, or building high-speed electronics for atomic physics systems. So that's what I think. I think it's important to kind of continue to do what we're doing now, where you have a strong interaction between, government sponsoring, new projects and new areas, and then industry slowly accepting maybe new materials and new applications as the driver for what they're doing.
Great. I think that's a great note to end on. So, so let's thank Jelena one last time for a really great talk.
Thank you.
So there will be the post-seminar discussion with Jelena, and the link is posted in the chat, and also on the YouTube page in the chat. The passcode is ATTOJoules, and I'm going to now take over sharing screen so that I can advertise next week's talks. So first of all, we always like to advertise our Sisters Quantum Science Seminar. And this coming week, next Thursday, will be Eugene Polzik talking about quantum mechanics in the negative mass reference frame. That's on Thursday at this time. I'll let you do the translation to your own time zone for yourself. And then on Friday, our next VAMOS talk, I'm very excited to advertise the first VAMOS postdoc double feature. So we're gonna do something a little different. We're gonna have 2 talks from 2 excellent postdocs. So we're gonna have Ivan Kozyrev from Columbia and Matteo Ippoliti from Stanford at the usual time, usual place. So we hope to see you all there. And thanks a lot. So hope some of you will join us for the post-seminar discussion, and hope everyone has a great weekend.
Thank you.